Pound for pound, these are some of the most powerful gaming computers on the market. But this man...
let's check out the announcements. As usual, we do have a PA and 3 quizzes doing this week. And in particular, it will be PA number 6, which is quite simple. If you completed PA 5, no problem. And then 3 quizzes this week. So relatively speaking, this week is going to be light. And this is done by design as well, because Polly was expecting you guys very busy in the midterm week. And if I can draw your attention to the course page, the schedule page in the course website, you will see that we are currently in this week. This is week number 9. We're supposed to be done with the pipelined RDTs, but we are not quite yet done. So we will go over the last RDT, the selective repeat today, and then start TCP. Okay, and you know what? In just one more week, which is 2 weeks from now, we will have the second exam. Okay, so that's to give you ahead of what's coming up. Okay, and we'll start from the selective repeat. This is the other pipelined IDT. If you recall the first one, go back in. It's one timer for a batch of packets, and if you receive an acknowledgement, that sequence number actually acknowledge all the packets before that. So it's the cumulative ACK, right? And when the timer times out, we retransmit the entire flight of packets that are still outstanding. Selective repeat is the opposite of it. We'll have one timer for each of the packets, if you recall in the overview. And therefore, if one of the timer times out, we retransmit just the packet. Okay? And the acknowledgement numbers in the acknowledgement packets we receive at the sender, it's only to acknowledge that particular packet. Okay? So that's why it's called a selective repeat, right? We will repeat or retransmit in a very selective way. So let's hear out the first video, the introduction of selective repeat.
Selective repeat. This is the second big categories of the pipeline RDT. So its design is pretty much the opposite of go back in. So in go back in, you have cumulative ACK. So the sequence number in the ACK there is to indicate all the packets before this particular numbers are received correctly. But in selective repeat, the acknowledgements are individual. So one acknowledgement packet per data packet. The sequence number in the acknowledgement is only to acknowledge one data packet. In go back in, we have one timer for an entire flight of packets. When that timer times out, we retransmit the whole flight of packets. In selective repeat, the opposite. We have one timer per data packet. When that timer times out, we retransmit just that data packet. Right? So, receiver will acknowledge each correctly received data packet individually. Sender will only retransmit a packet when the timer for that packet expires. Very straightforward. The slight tricky part of the selective repeat is at the receiver. Okay. We now have to buffer packets arriving out of order. The reason for this is very straightforward, very simple. If we send packet 1, 2, 3, and 1 arrive at the receiver, 2 get lost, 3 arrive at the receiver. You cannot be just extracting the data bits out of packet 1, pass it out to the upper layer, and not passing the bits of packet 2, and immediately pass the data bits in packet 3, and then later pass the data bits in packet 2, because that way you get bit sequences that is out of order in the application layer. And our definition of RDT is that all the bits arrive reliably and in order. So, receiver here in selective repeat, the implementation gets complicated. You need memory space to store temporarily packets arriving out of order. You wait until all the gaps are filled, and then you pass all the data bits up to the application layer in sequence. The only thing that remains the same is there is still this sending window. which is limited by n, from the base to base plus n. Now, be a bit careful in selective repeat though. What we are limiting there is the sequence number of the unact packet. So what is the maximum sequence number there? Can be unact. As opposed to in go back n, we say n being the number of unact packets. The reason that I'm saying you need to be careful is because of this. From the base to n plus base. Yeah, there are yellow packets, all right, and after the yellow packets, the blue packets. In go back n, they're just gonna be yellow and blue. So the number of yellow packets maximum will be n. In selective repeat, because we have individual acts, so some of the yellow packets can be green, like this. Right. So even though they're turned green, but that doesn't mean that they will include these 4, okay, into the window, like this. Okay, no. So what we're restricting is the maximum sequence number that can be an act, not the maximum number of packets can be an act. Okay, just to make sure that's clear. And the receiver of selective repeat is, as we talked about, more complicated. It also maintains a certain data structure, tracking the status of these packets. So we also have a window size here at the receiver. The base is now called the receive base. So receive base is always pointing at the first packet expected but not yet received. And there could be a number of these pink packets around. So these are the packets arriving okay, but out of order because there's a gap before it. So those are the out of order buffered packets. The blue ones are reasonable, okay, packets that are expected next. Okay. The black ones are just not possible. So if we receive packets after receive base plus n, we'll be just treating these as maybe hackers injected packets. Spoofed packets, things like that. And now the selective repeats finite state machines. This is the sender side of the machine, and this is the receiver side of the machine. And you might be going, wait, they don't look like FSM at all, right? Because previously we have like states, right? And the number of transitions like these. Yeah, what I'm doing here is to do textual representation. So what I'm saying is essentially, yeah, there are still 3 transitions. So first transition is triggered by this event, the data from above. Okay. Second, the timeout event. Third, triggered by receiving an acknowledgement packet within a particular range. So later on, you will see what's nice about writing the finite state machine this way, because it looks almost like a pseudocode, isn't it? Right? So the sender side is looking like a switch procedure, where when there's the data from above event switching in, then we do this. When there's the ACK packet being received switching in, then we do that. So now let's go over the finite state machines of the senders and receivers. Sender side, when there's a call from above, okay, if the next available sequence number is within the window, yeah, send packet. And you know how to do the next available sequence number, whether it's in window check. Right, so the next seq num should be less than base plus n. Second is the timeout event. If our timer times out, and that is for packet sequence number n, we retransmit packet n and restart timer. Straightforward. If we receive an acknowledgement packet, we extract the sequence number and check if it's within the send base and send base plus n subtracting 1. So that is saying, hey, whether the ACK is within the reasonable range, right? Because the send window is only this big. If we receive ACK before that or after that, that's just weird. Okay, let's just ignore those. So we'll only be handling ACKs that's within the send window. Now, once that's the case, we mark packet n being received, so turn it to green. If n smallest unact packet, so if n here is also the smallest unact packet, so we turn that into green. There could be a number of other greens following that. Then we could what? Advance the send base all the way to the next yellow packet. So advance the window base to the next yellow packet, which is the next unact packet. Right? So this is sender's actions, depending on what's triggering the sender's finite machine to take transitions. Similarly here at the receiver end, there are 1, 2, 3 transitions. First transition is if we receive a data packet that's within this range, the receive base and receive base plus n minus 1, so that is reasonable, okay, as expected. Then we send individual acknowledgement. So if it's packet n, then ACK n. If this packet is not expected, so meaning it's out of order, then we will buffer them. So these will be the pink packet, all right? Now, if this packet is actually coming in and filling one of the gray packet, so unreceived previously, but expected, then we can pass all the packets suddenly in sequence, all in pink, up to the application layer. So let's deliver those, okay, in ordered, and advance the window to the next, not yet received, but expected packet. So to the next gray packet. All right, so this is when we receive a data packet that is within the receiving window. If we get a packet, okay, that comes in, but it's actually in this range, receive base minus n to receive base minus 1. What is this? Okay. We are actually sending an ACK for that packet back. If you recall, it could happen, right? The ACK packet going back to the data center, if that packet is corrupted, the sender there is going to wait until the timer for that packet times out, then retransmit the data again. But that data has already been arrived at the receiver previously. And that's why the receiver sends an ACK back to the data at the first place. And that's before the data is found corrupted at the sender as well. Right? So in that case, we still need to send the ACK for that packet. Okay, do not ignore this. Otherwise, that timer is going to fire it again and again and again, and the sender there is going to retransmit the same packet again and again and again. Third transition, otherwise, or the default, I'll just ignore. Okay, so receiver, pretty much do nothing in case it's packet not within the receiving window or not one receiving window before. So those that are outside, just ignore it, because chances high that they're coming from hackers or previous connections, and the data somehow, the packet somehow gets stuck in the network for too long, and it's gonna be useless anyway.
All right, so that was the selective repeat. Let's check out the example. And this time, the example is much easier to understand, unlike the go back end example, which took us quite a bit time, isn't it?
And that's also a walk through an example of selective repeat, just like we did one for go back end. So that example in go back end is actually harder to analyze. This one, on the other hand, relatively easy. Now it looks very much like the example in go back end. So window size 4, and we start from base 0, and the next seek number 0. Getting a call from above? Yeah, because the next seek is less than base plus 4. Therefore, we generate packet 0 and send it out. And we go on until we hit next seek equals 4. And that is not smaller than 0 plus 4 anymore, so we wait. Over at the receiver side, scenario similar, receiving packet 0, but the receiver's action different. Okay, for packet 0, we send individual ACK 0. Receiving packet 1, we send individual ACK 1. Well, not getting packet 2, but we'll be getting packet 3, and out of order, so we buffer and send individual ACK packet 3. So ACK 1, ACK 0, ACK 1, and ACK 3 will go back to the sender. Now, sender, upon generating packet 0, packet 1, packet 2, and packet 3 will all start the timer individually. So T0, T1, T2, and T3 will all be ticking, no worries. Now, ACK 0 now comes back to the sender. Sender receiving ACK 0 will do what? Clear packet 0. So that packet will turn green. Is it in sequence? Yes. So we advance window. Yeah. Advance window by 1 to the next unacked packet. From receiving packet 1, also, yeah, advance sequence by 1 because it's in sequence. And hey, so base is changed to 1 and then to 2. So that allows us to send packets more, right? So 4 is generated, 5 is generated, and they are being sent out. Well, packet 2 did not get acknowledgement, but we get what? ACK for 3. All right. So what do we do there? Yes, we actually release packet 3. So we turn that into green. But hey, packet 2 there is still yellow. All right, so this green packet 3 is not the smallest NAC packet. So we cannot advance the window size further. We cannot advance the send window further or the base further. All right, so cannot be sending more. So still wait here. Okay, so this part of go back in and selective repeat similar. Right? But now, look, packet 4 and 5 will go to the receiver. Receiver here receiving 4, out of order again, buffer, send ACK4. Packet 5, buffer again, send ACK5. And those will go back. Here, timer for 4, timer for 5 will be fired because there's one timer for individual packets. So finally at this time point, timer for 2 finally expires and therefore we resend packet 2. Packet 2 goes out, received. Finally, this is the smallest NAC packet and all the packets subsequenting packet 2, 3, 4, 5 can be passed up in sequence to the application layer. And we send back ACK for 2. So, simpler.
All right, so that was the example. But one needs to be careful deciding how long is the sequence number given the window size. So this is a weird example of selective repeat that is going to draw your attention to how you design and set the sequence number space given the window size.
The last bit of selective repeat is this. Let me show you this case. There are 2 scenarios, okay? But from the reviewer's point of view, they will actually look the same. Right? And this is due to the fact that the sequence number here, the sequence number space, and the window size there is not set in a way that we could tell individual packets apart. Those who are sent earlier versus those who are sent recently. Okay, so the example goes, sequence number, only 2 bits, so there are only 4 different numbers. Window size, 3. Right. So the selective repeat sender side will look like this. Well, the window size is 3, so we can only send 3 packets back to back of each other. So packet 0, packet 1, packet 2 goes out. Receiver here receiving 0, 1, and 2. They will then send back ACK 0, ACK 1, and ACK 2. So ACK 0 here arrives back at the sender first. And this is in sequence, so we advance the send base. And we generate yet another packet to go. All right. And next ACK, that's going to advance the send base further to 2. Right? And we generate yet another packet to send. And the next one will be what? Carrying sequence number 0. Now, if packet number 3 did not arrive at the receiver, right? Receiver here will see, all right, I got the packet 0. And you know what? Within my window, I am indeed expecting someone carrying sequence number 0. So this one will be what? Buffered. And an ACK of 0 being sent back to the sender, isn't it? Right. So that seems to be fine. Yeah, this is the no problem case. Wait until you see the next one. Here's the next one. Same scenario, window size only 3, and we have sequence numbers. There are only 4 of them. So we send packet 0, 1, and 2 out. Receiver here generates ACK 0, ACK 1, and ACK 2 back. But unfortunately, all of them are lost. So timeout is going to happen and retransmit packet 0. This packet 0 will go, and receiver here will say, hey, you know what? I'm expecting packet 0. It's within the receive window. So buffer and send back ACK for 0. Sounds familiar, isn't it? Because that's exactly what's being done here in the first scenario. So from the receiver's point of view, identical. Also, buffer the packet and send back ACK 0. But the thing is this, at the sender side, you see, This packet 0 is a retransmission of the first packet 0. This packet 0 here is actually the second packet 0, no longer the original, the first packet 0. Okay. So if packet 3 here arrived at the sender, the sender is going to what? Clear that gap and pass 0 up to the application layer. Before that, pass, of course, packet 3's bits into the application layer. So 3 and 0's data bits will go to the application layer. But look here. Now, this is packet 0. When packet 3 finally comes here, it's going to clear and send packet 3's bits as well as this retransmission 0's bits up to the application layer. So you get unwanted duplicates. So you do have a situation here. From a receiver's point of view, it actually sees no differences in the two scenarios. You get duplicate data in the end in case B. So we need to be careful here to prevent packet 0 here and packet 0 here obviously are two different packets, but being confused as the same packet. Okay, so according to case A, we'll actually pass packet 0, these bits again to the application layer. Not good. So in order to tell this packet 0 and this packet 0 apart, we have to think, what is the worst case? Okay, can we use a sequence number such that we will not be confusing this packet from this packet? Okay, so a new packet should be farther away, should be carrying a sequence number that's farther away from an earlier packet. And no worries, if you look at this, case number 2, case B here, is already the worst case that I'm illustrating. So in this case, we're seeing that the receiver is advancing the receiving window one after another. So the receiver is saying, hey, everything is okay, let's move on. The sending side here, not getting any X back, hesitates and waits and waits and waits and not moving. So you have one end moving really fast and the other end staying. Okay? So you see in the end, the worst case is what? The sending window never really moved, but the receiving window moved the entire end, right? So they are actually end apart. If you want to make sure that none of the packets still in the sending window will be confused with the packets in the receiving window, what do you need to do? Is it obvious? The sequence number, make sure that the space is larger than 2 window sides, right? Then, hey, packet sequence 1 will never appear again in the next window, in the receiver's window. Right? So you would never have the trouble of confusing an old packet from a new packet. And that is why the sequence number space here needs to be larger or equal to 2 times the window size.
All right, so that was the tricky part about designing the sequence number space for selective repeat. For go back N, you don't have the same problem because go back N doesn't have a receive window, remember? All right, and that takes us to quiz 22. Okay, so what I'm gonna ask you in quiz 22 is asking you to compare go back N and selective repeat. So Q1 asks, which one of these will be sending more and using more network bandwidth for packet retransmissions? Okay, so which one? Q2, which one will be using more memory space at the receiver side? Okay. At the sender side, it's actually the same, right? For the window size, you actually need to keep a copy of the packets you have sent and not yet received acknowledgement. But the receiver end, there's a big difference. So which one is using more memory space at the receiver end? Q3, between the two of them, which one requires more timers at the sender side? Okay, so this one seems easy, right? Q4, if you are to program a pipeline RDT, okay, so that it's minimum effort, okay, which method would you choose to implement? Okay, So Q4 is a little bit tricky. Think about it. All right, so now let's move to the Slack space. W9-quiz 22 is already there. Okay, so you have some 6-7 minutes to work on. So let's start working on it. Find your teammates. Oops, sorry about the sound. The volume is obviously too high. Sorry about that. Yeah, and by the way, it's actually okay to be mistaken when you're answering these quiz questions. So it's better that you think it through. And if you forget about go back in already, maybe go back to the slides or go back to the videos from last week. Okay, that way it leaves a stronger impression so that you will do better in the exam. Okay, I see Xiang and Jason very quick. All right. So why don't you, team 1 and team 4, why don't you take a Q5 for quiz 22? Okay, if I ask you which of these two mechanisms you like better, can you tell? And can you give me also a reason why you like one better than another? Okay, that will be extra bonus. Okay, so team 1 and team 4. Okay, very interesting. Okay, so how about Keke? I forgot which team you are. Keke, if I ask you, okay, which one will be easier for you to understand? Okay, go back and select repeat. Which one? Well, I mean, implementation, minimum effort, right? It could be minimum effort in terms of memory, right? But is it minimum effort in terms of understanding it so that you can code it? Right? Before you can code it, you need to know the mechanism really well, isn't it? Okay, so Keke, let me find out which team you are. Which one will be easier for you to understand? Which one is easier? That's what I'm asking. Team 10, right? Yeah, oh, okay. So team 4, Amelia was saying, okay, so you actually like go back and better, personally, because the algorithm is easier to code. Okay, team 12, let's see. Yeah, go back in is the one we need to what? Retransmit a whole flight of packets, right? So obviously there will be packets you retransmit unnecessarily. So overall, you'll be using more bandwidth for go back in to retransmit for sure, right? We will need timers at the receiver, and you just hear the examples of selective repeat, right? So Q2 is obviously SR. Q3, wait a minute, memory required at the receiver end, and then we need more timers at the sender end as well in selective repeat. Go back in, I guess you guys all say kind of go back in requires less effort because you don't need so many timers. You don't need to maintain an array of timers at the sender side, and you don't have to maintain an array of packets, okay, at the receiver side of selective repeat either. Okay. But you kind of see also that between selective repeat and go back in, it's like it's not clearly that one mechanism is better than another, isn't it? Okay. So go back in, although sounds a little bit more complex, and it took us more time to just walk through an example. But it's less memory required, okay? Less stuff you need to manage, so it might be a better choice to implement. Bo Sheng, okay, let's see. I think Bo Sheng is catfish. Yeah, okay, similar because receiver doesn't need to store arrival packets. Okay, so very interesting. Team A is saying that you need less memory for the timers, and Team 14, although both choose go back in, but Team 14 is saying that you need less memory to keep packets at the receiver end. Yeah. And I think Howard, go back in, selective repeat, go back in. Go back in because it requires less timer. Alright. No need to set many timers. Yeah, so it does require less memory, but some of you don't like that it's having multiple timers. Some of you don't like it because you need to manage the memory space in the next packets to come window at the receiver. Alright. Okay, good then. Yeah. So I guess you got it. That's the main difference between the selective repeat and go back in. Okay, one seemingly straightforward, easier to understand, but it does require individual memory space for each packet for out of order delivery for timer. Okay, good. So that's quiz 22. Let's move on, and we are finally starting TCP. Well, until now, we've heard about many versions of RDTs, from the stop and wait RDTs, and earlier today and much of last week, go back in. These are the pipelined RDTs. We know that reliable data transfer is implemented in TCP, one of the two transport layer protocols. But exactly which of these RDT is TCP using? We'll learn, okay? Getting to know more about TCP. So this first video, about 6.5 minutes, it's an overview of TCP. It will sound familiar, and yet you will also hear something that's a little bit new.
And this is 3.5, connection-oriented transport, particularly the TCP protocol. So in this particular section, we're definitely going to talk about the RDT implemented in TCP. Now, provided the background, okay, very extensively in 3.4, you should be able to understand TCP's implementation of RDT, TCP's design of RDT. Now, in addition to the RDT in TCP, we are also going to talk about the packet format of TCP. And that is what the segment structure meant here by the textbook authors. And then there are two minor functions, but necessary functions in TCP. One is called the flow control. The other is called the connection management. And this is the overview. TCP we know already. Just like UDP, it's what? End-to-end process-process communication. So end-to-end there can also be referred to as point-to-point communication. We have a sender process and a receiver process. Now, in this connection here, what we're doing is to do reliable and in-order data transmission. Now, what's a little bit unusual when we talk about TCP is this. Instead of earlier, when we were talking about the general principles of RDT, we are counting the data by what? Packets. Packet 0, packet 1, packet 2, packet 3, so on and so forth. But in TCP, we count data all right, but we count the data by the bytes. By 0, by 1, by 2, and so on and so forth. So that connection here, when we are passing data around, we are actually passing a stream of these bytes. Right? So there's no more message boundaries, or there's no more packet-to-packet separation. Right? And last, this is actually telling you ahead of time that TCP's reliable data transfer is doing this, the pipeline-based RDT, so that we have a window size there, where the size n is definitely larger than 2. And so we could have multiple packets in transit so that the utilization of the connection there can be higher. Now, what we don't know quite yet is this. This window size is also used not just for reliable data transfer. Later on in section 3.6 and 3.7, you will also hear it's also for the congestion and flow control. Okay, so there's going to be a window size for flow control. And the window size for RDT is also used, okay, for congestion control. And conveniently, in flow control, what's being done is the receiver will every now and then tell the sender, hey, you might want to slow down or you might want to speed up, depending on how much the buffer space is occupied at the receiver side. You see, what happened at the receiver end of the TCP is this. Data will come in continuously from the sender. Data will be extracted and passed up to the application layer process. So there's an incoming rate and there's also an outgoing rate. When the outgoing rate is slow, incoming rate is fast, then you see the buffer space is quickly exhausted. Okay, so at that point, receiver tells the sender, hey guys, slow down. Now, the other way around, if the buffer space is very empty, then telling the sender, feel free to send more. So full control there. Okay, mainly allowing the receiver to tell the sender, hey, slow down or speed up, such that there's no congestion occurring at the receiver side. Because if the incoming rate is high, outgoing rate is slow, over time, when the buffer is exhausted, the incoming data will be what? Will be dropped. Okay, so delay long, and you see also data loss there, right there at the receiver. So this is to avoid also congestion. But it's a bit weird. It's actually to avoid congestion at the receiver side, not quite in the middle of the internet. So when I say in the middle of the internet, I actually meant congestion in the core of the internet. Sender process, receiver process is what? At the end of the internet, at the edge of the internet. So flow control there is to try to control the end processes such that there's no packet drop at either end. Congestion control, on the other hand, is to control such that there's no packet drop or congestion in the middle, in the core of the internet. And TCP, being connection-oriented transport layer service, is sending some messages in the beginning before data can be transmitted. So there are some handshaking being done right before the data exchange. And these handshaking messages are there to set up the initial states of the sender and receiver. And that is called the connection management part of TCP. Last but not the least, there's a mindset change here in a TCP connection. Data traveling in a TCP connection is now full duplex. What I meant by that is the data flow is going, bidirectional. Okay, so two processes or point-to-points, will be sending data this way as well as this way. Now, why is this a major mindset change? If you recall in 3.4, when we were talking about these reliable data transfer mechanisms, we always say what? This is the sender side of RDT, this is the receiver side of RDT. What we are saying there implicitly is also, this is data sender side of RDT. This is the data receiver side of the RDT. Data receiver there, receive data. It transmits something as well, but it's transmitting only what? The feedback messages, the ACK messages. The receiver there does not send data. So TCP here you see being more general. Data can go either way. So the two processes will be implementing both sender and receiver finite state machines. And the last bit is this. MSS, a special term that is referring to this, the maximum segment size. If you recall, a packet at the transport layer is called a segment. So maximum segment size is essentially the maximum packet size. In reality, in actual TCP implementation, we're still sending data packet by packet. But the sequence number we'll be checking to do reliable data transfer is now counting the bytes of the data, not the packet numbers of the data.
All right, so next video is talking about TCP's packet format. It's quite complex. We're gonna need 6 minutes, so we'll run over just maybe 10 or 20 seconds. So
TCP segment structure, aka the packet format. It does look a bit complicated, definitely more complicated than the UDP packet. If you recall, in UDP we do have these fields: source port number, destination port number, as well as the checksum. So all these are what called the header fields. So in TCP packet, the header part is substantially larger. While the data part, it's still variable lengths that could be large, could be small. So the overall structure in TCP packet is actually very similar to UDP, two parts, header and data. The main difference is where? The header part. So some of the header fields repeat itself. We see source port number and destination port number as well as checksum also in TCP packet header. But what else in the UDP packet header that we don't have or we do have in TCP's packet header? And here's UDP's packet format. So we do see source port number, destination port number, checksum. And what else is in UDP's packet header? The length. So that is the entire packet size, including the header as well as the bytes in the segment. So data and header together, in this field, the length. And do we have lengths here in TCP's packet header? Well, if we look around, something slightly similar. It is lengths. So LEN is actually short for length, but it's only the length of the packet header. So this part versus UDP's length, quite different. Semantic, very different. So UDP's length actually talk about the entire packet size, but length here is only covering the first part of the entire packet structure, the header length. Do we have lengths in TCP's packet header? We actually don't. The thing that we have the closest is this, the header length. So the length in TCP packet header counts only the size of the TCP packet header, while the length in UDP's packet header counts the entire UDP packet. Given that we're already talking about the header length, why don't we talk about these special bits, special flags in the TCP packet header? First is the A flag. Okay, so this is called the ACK flag as well. When it's turned on, when the ACK flag is on, that's indicating that the acknowledgement number here is actually valid, meaning that the sender of this packet is trying to tell the receiver that it's trying to acknowledge certain bytes being received. And these three R, S, and F bits, they are there to indicate packets being used to do connection management. So for example, SYN here, the SYN packet is to set up connections. The FIN packet, which is Latin for the end, yeah, conveniently, okay, is to tear down a connection. RST, or the R bit here, means reset, that is to re-establish the connection, to re-initialize certain parameters between the sender and receiver of the TCP. And P bit, yeah, P stands for push, that is to push data now. So this is to actually pass the data out as soon as possible, but it's generally not used. Just like the U bit, this is urgent, so this is indicating that whatever data is here is urgent. So pass it out through the network or to the application layer as soon as possible. Okay, so you see urgent, the purpose, and push, somewhat similar. The ambition of the network engineers much early on is also that hopefully a data network or the internet can also allow urgent data being sent, just like we could make it 911 call, or in Taiwan 110 call to get police's attention or the fire department's attention as quick as possible. But unfortunately, the way the internet is designed is just not very good for urgent, critical data transmission. And yeah, we said that these are not used, so there are a number of bits not being used. But the fact is actually there are two more bits being used. It's called the C bit and the E bit. Now these two bits are not really for reliable data transfer service, not for connection management purpose. They're actually there for congestion control. Okay, but it's not quite the congestion control implemented in TCP though. Okay, it's just that the engineers are expecting, okay, later on TCP's congestion control can be extended, okay, together with the core of the internet such that we could do better control. So there will be two more bits we'll have to talk about, but it will be at the end of chapter 3. And that takes us to, the urgent data pointer. So this is actually working with the urgent bit. When the urgent bit is on, then the transport layer of TCP is going to look into this pointer and then grab whatever the data that's here indicated by the pointer. So this data here will be extracted and passed out as quick as possible. And receive window here. Yeah, this is the window size for the flow control. Okay. If you recall earlier in the overview, we say flow control is for the receiver to tell the sender, hey, slow down or speed up. And when the slowdown is to be communicated, receive window here will be a small number. If the receiver wants the sender to speed up, the receive window there will be larger. And the last two fields in the header are these. The sequence number as well as the acknowledgement sequence numbers. So these are exactly for the reliable data transfer purpose. But keep in mind, we're now counting the bytes, okay, not packets.
All right, so these should set the stage for tomorrow's lecture. So we'll definitely talk a lot more about TCP, okay? All the necessary components for TCP's RDT to work. And with that said, there's just one announcement that I neglected to mention at the beginning of the class. Tomorrow noon, there is a important department level meeting that Polly needs to attend. So we'll have to cancel the office hour for this week. But feel free to type up your questions on Slack. Okay. And that's all for this week. I'll see you tomorrow. That's all for today. I'll see you tomorrow. Bye. Okay, Catfish, let me stop the stream and I'll attend to you as soon as possible.